You know that feeling, right? When a single piece of new information just clicks and it completely changes how you see a situation? One minute, anything seems possible. The next, you get a clue, and suddenly the whole picture snaps into focus. Well, today, we're going to dive into the math behind that exact aha moment.
So this is the big question we're tackling. Think of us as detectives for the next few minutes. We're not just calculating odds in a vacuum. Nope, we're learning how to adjust our thinking, how to recalculate when we get a piece of evidence that changes the entire game.
All right, let's get into it. The main idea here is actually pretty simple. When you learn something new and concrete, the world of possibilities literally shrinks, If I tell you I'm thinking of a number, it could be anything, but if I say I'm thinking of an even number, boom, you just threw out half the possibilities. We need a way to figure out the odds inside this new, smaller world.
And it has a name, of course. It's called conditional probability. The key phrase you got to listen for, the trigger word, is given that. The second you hear that, it's a huge signal that we're not looking at all the possibilities anymore. We're focusing on a very specific slice of reality.
This is just a fantastic way to picture it. The thing you know has happened, that event E, it becomes your entire new universe. We call it the new sample space. It's kind of like zooming way in on a map. You can just completely ignore everything outside that little box because you know for a fact the answer has to be inside it.
So how do we actually calculate this? I could just flash a formula on the screen, but where's the fun in that? Instead, we're going to build it up piece by piece from an idea that I think you'll find is super intuitive. Okay, so imagine you're running some experiment over and over again. First, you just set aside all the times your clue, event E, happened. That's your new, smaller pile. Then, you just look inside that pile and count how many times the thing you're really interested in, event F, also happened. See? The probability is just that ratio. It's the part divided by the new whole. And when you take that simple idea of the part over the whole and write it out using the language of probability, you get this really elegant and super powerful formula. It just says the probability of F, given E, is the probability of them both happening, divided by the probability that your clue, E, happened at all. Let's make this concrete with a super simple example, rolling a die. So event A is rolling an even number. That's a 1 in 2 chance, right? Event B is rolling a 3 or higher, so 3, 4, 5, 6. That's a 2 in 3 chance. And the chance of getting both, an even number that's also 3 or higher, well, that's just rolling a 4 or a 6, so that's a 1 in 3 chance.
Okay, time to use our formula. What's the chance of getting an even number, given that we know the roll was a 3 or higher? We plug in our numbers, and we get 1/2. Makes sense. Now let's flip it. What's the chance of rolling a 3 or higher, given that we know it was an even number? We plug those numbers in, and we get 2/3. Different answers.
And that brings us to a really crucial point. This is so important. The probability of A given B is not the same as the probability of B given A. The clue you get, the condition, it fundamentally changes the question you're asking. And because you're asking a different question, you get a different answer. The order really, really matters.
So this leads to a pretty fascinating problem, doesn't it? What if you know one of these conditional probabilities, but you actually need to find the other one? Is there some way to, flip the script?
Think about it like this. A doctor probably knows the odds of seeing a certain symptom, given that a patient has a particular disease. But you, the patient, you want to know the opposite, right? You want to know the odds you have the disease given that you have the symptom. It's a classic problem of reasoning backwards, and there's a brilliant tool designed to solve it. And that tool is the famous Bayes' theorem. It is the mathematical rule that lets us do this incredible flip. It gives us a logical way to start with the evidence we can see, the effect, and work backward to figure out the probability of the thing that caused it. It's incredibly powerful. So you know what? Let's put this theorem to work. It's time to solve a little mystery. We're going to see exactly how Bayes' theorem helps us update what we believe about the world when we get hit with new data.
All right, here's our setup. We've got a factory with 3 machines. Machine X is the big workhorse. It handles half the product, but it has a 3% error rate. Then you have machines Y and Z, which handle less volume, but they mess up a little more often. These are our starting facts. This is what we believe about the system before anything happens.
And here's what that belief looks like. If you just grab a random part off the assembly line,
With no other information, your best bet is that it came from machine X. A 50% chance. It's the obvious first guess, right? But then we get our clue. The single critical piece of new evidence. A quality inspector walks over and says, "Hey, I found a bad one." This is the effect. Now, we need to find the cause.
So here's the mystery we have to solve. Now that we know this array is defective, does that change our guess? You might think, well, machine Z has the highest error rate, so maybe it's the culprit. But it also makes the fewest parts. So how does this new fact change our initial beliefs?
And this is where Bayes' theorem comes in to save the day. So for each machine, what we do is we take its specific error rate and multiply that by how many arrays it makes. Then we divide that by the overall chance of finding a bad part from any machine in the whole factory. And when we run those numbers for all three machines, we get these new, updated probabilities. And this chart just shows that shift in our beliefs so clearly. Look how things have changed. The gap between the machines has shrunk. The new evidence, the clue, has made us less sure that machine X was the source and has increased our suspicion of Y and Z. But here's the really fascinating takeaway. Even though its probability dropped, and even though machine Z has the highest error rate, machine X's massive output means it's still the most likely source of any single bad part. Our belief was updated, it was refined, but it wasn't totally overturned. And really, this slide gets to the whole point of everything we've talked about. The quote nails it. This isn't just about math problems. It's a formal system for learning. It's a logical, structured way to take what you think you know, get new evidence, and come out with a smarter, more refined belief.
Honestly, this is such a powerful way of thinking, and it applies to so much more than factories or rolling dice. It's really about being willing to adjust your worldview when you're faced with new facts. So, I'll leave you with this question. Now that you've got the tool for updating beliefs, what belief will you update next?